To introduce today's speaker, Shikma Zaarur. She received her PhD in 2014 from Yale University, where she happened to be my own student. She is now a postdoc working with Yigal and Isotopes here for the last, 2 years?
2 years.
Shikma, well, before that she did a short postdoc at MIT with Shuei Ono and Tanya Bosa. And she'll be talking about hydroclimate regime in southern China during the last glacial period, etc. Long title. Tomorrow we have a special seminar by Huguangyan Maar, who will talk about microbiology in the Earth system, impacts of on environmental processes. This will be in this room at 10 o'clock tomorrow. At 12 o'clock, the Kao seminar by Guy Dagan. He'll be talking about cloud field lifetime as a key factor for evaluating aerosol effect on climate.
Thank you. So thanks, Chagit, and thank you for being here. And so as Chagit pointed out, this is a long title. So the first thing I'm going to do is to break it down. So what we're ultimately looking for is to understand climate in South China or East Asia during the last glacial period. We're going to be looking at sediments from Huguangyan Maar lake, and I might be referring to this lake later on as Hug for short. And the main component that is going to be telling us the information about the climate through the lake sediments are strontium neodymium isotopes, and I'll sort of talk you through that and walk you through that. So we're not working in a vacuum, and when we're wanting to understand what the climatic regime was and how we can understand what the climate was in the past, we're also looking at what other people have done, and there's been plenty of studies done in this area. This is a very hot topic. Two big groups of data or scientific groups come from information from the Chinese Less Plateau, the Less sequences, and from Speleothems, cave deposits. The most famous one is Hulu Cave, but there's also a nice record in Dungan Cave and some other caves in this region. Our lake is located here. And so I'm saying climate, but let's just, for a second, see what is the climate system that we're looking at. And I won't go here into too much detail, but we're basically looking at the East Asian monsoon, and we're looking at winter versus summer. And the main thing I want to draw your attention is that the winter monsoons bring cold air from up here down south, and that goes over the continent and has the potential of maybe bringing dust. And the summer monsoon, which I think are more famous, and that is what we see in the news, all the floodings in East Asia, bring warm, moist air from the oceans to the continent. This area where the lake is, here in southeast China, is also, to a lesser extent, influenced by the Indian monsoon. So the Chinese Less Plateau has these less sequences, and these are less paleosol sequences. And there's different parameters that are looked at. But one of the things that is interesting, and I'm not going to go into all the studies that were done, is that if you look at what are the variations that we see in terms of climate signals when the different proxies in the sequences are interpreted for climate, is that we're seeing what is interpreted as monsoon variations that go with the glacial cyclicity. And so what we see here is one of the plots, and I'm not sure where the reference for. This is from Tao et al. 2007, and what they're showing here is variations in the in one of the parameters that they were looking at. And early on in the Pleistocene, when glacial cyclicity was 40,000 years following obliquity, that is the signal that is observed. And after the Pleistocene transition, the main signal that is observed is eccentricity. So that is, in terms of climate forcing and what is observed in the record, that is, in general, what the less sequences are showing.
Shikma, what's the signal?
Here they're looking at magnetic susceptibility, but they look at a lot of chemical compositions. I'm specifically not did not choose to look at all the different proxies, but just to show that almost all proxies that are used in the sequences show glacial variability. So that is obliquity deeper in the core, deeper in the sequence, and eccentricity higher up in the sequence. The other major source of information or archive that is used are speleothems, as I mentioned, from these caves. And this is the data from Hulu Cave. And here I actually will go a little bit more into the signal. And so what is plotted here is age on the x-axis. This is 7,000 to 10,000 years. And I'll first concentrate here on this y-axis, which is the oxygen isotope composition of the speleothems. And you can see all these different colors, they're all from the same cave. They're just different pieces of this, different pieces there. And what we see is that there's fairly large variations in the isotopic composition. What Huguangyan Maar, or the way Huguangyan Maar interpreted this variation is to come from the different sources of the rain that feeds into the caves from which the speleothems precipitate. And for those of you who are familiar with oxygen isotopes, the composition of the isotopic composition of the carbonate itself is depends on temperature, and so temperature variations using the same water composition from which the carbonate precipitates would result in variation. And the source water, if there's the different isotope composition of the water would affect the composition of the carbonate. And what they're saying is that the majority of the change comes from the sources, whereas the summer monsoon have a lighter isotopic composition, and the axis here is in reverse. So these are lower values, and these are higher values. So when we have these values, it means that the majority of the water comes from the summer monsoons, and when we have higher values, or values down here, this is the influence on the winter monsoon. On the other side of this plot, where we have the insolation at 30, so where the cave is at, and what they're saying is that, or showing, is that the variations in the isotope composition in the speleothem generally follow the insolation in this area. The insolation in this area is mostly driven by the precession cycle, and you can see that by the 23,000 year cycle here. And so there is an agreement between what we see here and what we see here, and that they're both different proxies in these records seem to be reflecting changes in the East Asian monsoon systems. But there's also a disagreement, and that is for the climate drivers. So, as I mentioned before, most proxies, the vast majorities of proxies looked at in the Chinese sequences show glacial cyclicity, which is eccentricity and obliquity. And further south down here in the caves, we mostly see the precession. And there are two possible explanations in general. One, it could be geography, like where are we long lat? So some areas, just by where they are, would be influenced more strongly from one force, from one driver versus the other. And the other thing could be climate. So Yeshua asked, well, what was the proxy? Sorry, it could be the proxy. So Yeshua asked, what was the proxy? When I say proxy, there's two things that I'm thinking about. One is the material itself that I'm measuring. What is it that I'm measuring? So here we might be looking at less than paleosols, or we might be looking at different minerals in these sequences. And here we're looking at carbonate precipitating from solution. So there's the material itself, and then there's the process that makes the proxy. So either sedimentary or sedimentation, or the chemical precipitation itself. And so these have been discussed in the literature as two potential sources for the difference or discrepancy between what we see in these records. So that is the climatic framework and the big questions in which we're working. And as I mentioned, I'm going to be now trying to add a little bit to that by looking at Huguangyan Maar sediments. So what is a maar? What is a maar lake? For those of you who are not familiar, it's a lake kind of like Birkat Ram if you've been, and that is a lake that is formed in a crater of a volcano. And there's something very unique and helpful and good for us, for our purposes in these lakes, is as you can see from the picture of the lake here, it has a very, very small drainage system. So it doesn't drain any big lake, any big rivers, anything, any solid materials that are going to be found within the lake sediments have to either come from the rim of the lake or have to be wind blown, because it doesn't drain anything else from around. And so there was a big Maar Lake drilling project in China, and Huguangyan Maar was one of the lakes that was used in this drilling project, where they went and drilled in a whole number of Maar lakes to look at sediment cores. In terms of the climate system that we're looking at, and I mentioned that before, we're mostly affected by the East Asian summer monsoon, to a lesser effect by the Indian monsoon from here, and today also the winter monsoon can reach this area. Geologically speaking, where we are, I said we're sitting in a volcanic field, or the lake itself is in a volcanic crater, and this will be more important for later on, but I just wanted to look at this and have this in mind already now, is that the lake is here in this volcanic field, surrounded by Quaternary alluvial and fluvial sediments. And this is an extension, so there's an opening here, and we have granitoids on both sides of this field. The first comprehensive study on this Maar Lake was done by published by Mingra Medal in 2004, and that was part of that comprehensive drilling project that happened in all over China. And they drilled a number of cores, and they did all the dating, and they have a fairly thorough description of the sediments itself in terms of what the sediment is made of, basic chemical composition and mineralogy. And they were, of course, looking also for climate variations. What they found is that when, this is a complex plot, so I'll just point you to a few things. What they found, and first one in the look here, is that when they look at all the different components in the sediments, and that is the particle size, the general chemistry, organic material, what is in the organic material, they could separate the sediment into 7 lithozones, marked here as LZ1 to LZ7. And they tried to see if those match any of the big global climate events or anything like that, but they didn't. So they could see variations, but they didn't really go, none of these lines really matched well with major climate events. The only proxy within this record that can directly be linked to climate is the pollen. And I marked here the most obvious one, which is the change from temperate pollen to tropical pollen. And what we can see, and I marked here the glacial, going up to the glacial maximum towards the post-glacial, is that during the peak glacial period, we see an increase in temperate plants, and during that time, tropical plants disappear, and then it reverses. So we do see a climate signal in the lake, but this is a very low resolution response to climate. And so it wasn't very helpful in trying to, by looking at these parameters, we couldn't really see none of the climate forcings. We can't see any precession or obliquity or any of those in the pollen record, or also the shorter millennial scale climate events. The claim to fame of this lake, or when it made the headlines, is in a study published in 2007 in Nature by Encheva et al., where they looked at sediments from the core, and I'll go into a little bit more detail in the next couple slides, and connected the influence of the ITCZ to the East Asian monsoon by using the record from this lake. And basically what they did, and these plots can be overwhelming, so I highlighted here the most important part of the plot right now, is that they looked at a 16,000, here they only had the 15,000 part of the core, and they looked at titanium counts in the sediments. So these are not concentration, these are counts per second from the XRF measurements. And they saw variations in the titanium. And they also saw that these variations in titanium correlate with millennial scale events. So we have the boiling Al right here, which is a wet period, and we have the Younger Dryas here, which is a dry period in this area. And they said, well, high titanium counts must be related to dust, because titanium is used in other records to reflect dust sources. It is a conservative element. And so they said, high titanium dust means that there is a high dust influx into the lake. And a high dust influx into the lake means that there's a strong winter monsoon, so that these monsoon winds are strong and the summer monsoon is weak. When we have low titanium counts in our record, that must mean that there is a low dust input into the lake, and therefore a weak winter monsoon and a stronger summer monsoon. And that was, and this here was something that they just stated. This was their conclusion. So let's go back to this plot, and now add to it, with these variation, the strong and weak winter monsoons that they interpret. They also compared their record to regional records. So I pointed before to Hulu Cave and to Dunga Cave, and these show the same pattern in their oxygen isotope composition. So we have the isotope composition here, and we have the winter monsoon and the summer monsoon, and that actually fits fairly well with what Yancheva and Al said. So they said wet with wet and dry with dry. I'll get back to that a little bit later because there's some problems with that. The third important paper that I want to refer to in terms of the many papers that were studies that were done in this lake is the study of Zhu et al. In 2009, which was almost a response to the Yancheva study. And what they did is that they looked at the strontium and neodymium isotopes in the lake sediments. And I'll explain in a few minutes a little bit more about the system. But what I want to point out here is sort of the bulk of their results. And so on the x-axis here we have neodymium isotopes, and on the y-axis here we have strontium isotopes. And what you see are different fields for different materials. So here are the sediments that they measured, marked here in red. Down here is the volcanic material from the lake rim, and a soil from the vicinity. And way over here are the isotopic composition of the less deposits in China. And so just by looking at this like that, we can see that the isotopic composition of the lake sediments is more related, or very closely related, to the volcanic material, the local volcanic material into the lakes. They did calculate and estimate that up to 17% of the signal observed here in the lake sediment could be attributed to contribution from the less samples. One major problem with this, in terms of what we want to look for, is that these were only surface sediments, and so it's not a core. So this is a distribution on the surface, and the surface actually might be disturbed by human activities in the lake. But it gives us a framework in terms of the players that might be at hand here in terms of contributions to the lake. So what am I doing in all of this?
May I?
Yes.
A mixing line will be affected just as much by the concentrations of those elements as by their isotopic composition.
Right.
So
I'll talk a little bit about that in a little bit, but this is just what they found in terms of...
In what were the less compositions measured?
You mean here? These?
Yeah.
These are in the less deposits.
In what? What carries the strontium in the neodymium?
I'm not sure which. I think they just look at bulk less materials. They went. These are from these studies, and from what I remember from looking at the raw data, these papers have also size fractions, some of them, but these values, if I remember correctly, are the bulk values for the sediments. So what am I going to add to this? So there's the first question that we want to ask in the Yancheva and Zhu et al. Sort of frameworks are, can we actually identify any dust or aeolian input into the lake sediments? Then we want to see, well, if we can, what is the source? Is it the less deposits or some faraway source or something else? And ultimately, as we said, can or how we identify any climate variations in the record in the lake sediments? So we have 3 sets of samples from the lake. We have the core sediments from the Mingram et al. Drilling project. We have samples collected that Moti and Eagle collected when they were out there from the lake rim. And so these include basalt, pyroclastic materials, and some paleosols in the sequence of the lake rim itself. And then we also have a suite of samples collected outside the hydrological drainage. So outside the lake area, about 1.5 kilometers away. So we have to build this up. We can't just look at the isotopes. And so let's just first examine what we're looking at. In terms of the lithology, the lake sediment is Jaitya, which is an organic rich sediment, and we have up to 40, and in a couple cases even slightly higher than 40% organic matter content. The rim itself, as I mentioned, is volcanic, and the nearby samples are soils. In terms of mineralogy, can that tell us anything? Well, as expected, the rims have a volcanic basaltic composition. The sediments are a mixture of clay, mostly a mixture of clay and amorphic material. And then in the nearby soil, we're seeing clays, but we also see a significant amount of quartz. Can the chemistry tell us anything more? And there's a lot of chemistry that we did on the core. I chose just a few things to show here. And I'm going to concentrate on the titanium predominantly because that was also what Yanchev et al. Looked at, and there were big conclusions that were made regarding the titanium. And so the first thing we're going to look at, and I'll get to that plot in a second, but the first thing we're going to look at is the titanium here on the y-axis versus aluminum, and we see that they go really well together. And this titanium, aluminum, and iron, actually, which I'm not showing here, they all go together in the lake sediments. If we put these 6 samples aside just for a second, and these happen to be the 6 youngest samples, and I'll kill the suspension now. I don't have a specific reason for why they show a different trend yet. But if we just put these 6 samples aside for a second, we actually have a really, really strong correlation. So I'm fairly confident that whatever is causing the aluminum enrichment in the sediment is also causing the titanium enrichment in the sediment. Now let's start adding the different materials that we have. So we have the basalts and tuffs and paleosols from the lake rim, and this is their isotopic composition. And now I'm going to start referring you also to this plot here that shows titanium to silica. We have those nearby soils. They plot here and up here. And then we have, remember I showed those granites in the geological map before? We have the granite here, and we have the less deposits here. And so we can see that not only the titanium goes with aluminum, we can see what we would expect in terms of the rock types. The titanium silica sort of evolution here, but that the sediments on top of that are enriched in respect to any of those. So if we have this granite to weathered basalt or weathered material here, the sediments are much more enriched in silica. So another way of looking at the data is to look at the CIA index. If we're looking at weathering process, perhaps, that might be the reason for the enrichment of the aluminum. Let's look at the weathering index. And we're plotting things here to the CIA index, which looks at aluminum in respect to the soluble materials, so calcium, magnesium, and potassium in this case. And we can see that the sediments are very weathered. The lowest CIA index in the lake sediments is about 84, and the highest is 97. When we add the paleosols and the nearby soils, we see that the nearby soils are not very rich in titanium, but are very, very weathered. And the paleosols from the lake rim are here. And if we add all the other materials, we see that the sediments are very weathered, and maybe they're sort of an extension of some of this here. And so by looking at these, we can say, I think like I can say with fairly good confidence, mostly from this sample here, and I'll just go back for a second here, is that if Yancheva and Al are going to say that titanium indicates dust input, the less can't be the dust input, because if titanium would be enriched with dust from this, dust from here would actually dilute a local signal, because you're trying to enrich with something that is poor in what you're trying to enrich with, if that makes sense. So that was a little bit of the more major elements. Let's see what the rare earth elements can tell us. And so for those who are not familiar with these plots, we have the rare earths here, and samples are normalized to chondrite. And before I show any of the samples data, I want to just help you tune your eye to what we're looking for. And so this is the local basalt, marked here in black, and this is a fairly typical plot for basalt. The Cathasia granitoids have this EU anomaly here, and so what we're looking for is this anomaly and also the change in the slope. You see that this is a steeper slope than here. And then the less actually is similar to the granite, and that is the granitoids, and that is not surprising, as less is usually is actually weathered byproducts of granites. So I chose here two samples to show. One is from the rim and one is from the nearby soil. And what we have here is in the bulk orange line is the bulk material of a pyroclastic sample from the lake rim. And the bulk sample looks mostly like basalt, but we also separated fine fractions because the pyroclastic material had other things mixed in it. And when we separated the fine fraction, the smaller than 100 microns, and did this analysis on it, we actually saw that the fine fraction has a different composition that resembles more the less or the granitoid composition. Looking at the nearby soil, and I gave here sample number 10 just for example, here we see the opposite. The bulk composition of the sample, of the material, actually has more of a granitic characteristic. And as we move into the finer fractions, they look more and more basaltic. So the REs are now starting to tell us that there is something here in terms of possibly two sources with two very different compositions. Looking at the sediments, however, and I separated the sediments here to group just so we can see it, they all look basaltic. So within the sediment in the lake, we're not seeing, there's possibly not enough resolution to look for these particles. And a fair question to ask would be, well, did you look at the fine fractions? Well, we tried, except for these were all unimodal. So we measured the size fraction for the lake sediments, and there were no fractions to separate. Everything had a unimodal, pretty much normal distribution. So we have the lithology, we have the mineralogy, we have the chemistry, and the chemistry now is telling us that the rims are volcanic. The sediments are mostly weathered and basaltic in composition, and those nearby soils are fairly weathered, but they're granitic in composition. What can the isotopes tell us? So I'm not going to go into too much detail here, but just sort of to give an explanation of how this works is that, and I'm showing this here on strontium, is that we have the way the different compositions develop in the rocks is that we have the mantle composition, and then wherever we have high rubidium, strontium, the crust will sort of evolve along this line as time goes by, and then we'll get a depleted mantle with lower rubidium, strontium composition. And that results ultimately in, and this is sort of an extension in just general numbers, in, for example, young basalts that would have this composition and an evolution line that eventually will get old granitic rocks will have this general composition. And so in China, for instance, how is that used? So Chen et al. In 2007 did what I think is a fantastic job at sort of mapping out the isotopic composition of the different deserts in China. And I clumped together different deserts because they had a whole bunch of different ones here. But you can see that if our young results are here, the desert, for instance, in northeast China, which these deserts here, have this composition. In central China, around here, they have a wider range of composition and they're more radiogenic. And in West China, over here, we have this composition. And so two things I think I'd like to point out from here is one is different as the evolution of the isotope composition happens in the rocks, different rocks and different sources or different sediments will have different compositions, but it's not a one solution to a problem because you can actually have overlapping compositions. So you can't just measure a sample, see a value and say, bingo, my sample is from here or from here, because you actually also have to look at the bigger picture and be able to say, well, which one of those is more plausible or more likely to be what I'm looking for. In our content, and this is for you, Yesha, you ask for concentrations, so here you go. So we have, I'm going to start first with just the strontium, and so we have strontium concentration here on the x-axis, and the isotopic composition here on the y-axis. And here are the nearby granitic soils, and here is the volcanic material from the lake rim, and here are the core sediments sitting nicely on a mixing line between these two end members. And we can see that they're mostly influenced by the volcanic rim, which also makes sense from the setting, but something is drawing them up towards the nearby soils. If we look at this in the strontium-neodymium space, then now we have epsilon neodymium here on the y-axis and strontium here on the x-axis. We see a slightly more complex picture. And so the samples from the lake rim, so that is the basalt and volcanic materials and paleosols, form this field over here. The nearby soils, and I'll explain in a second for why there's more dots here than those three that you saw before, form this field over here. And the lake sediments are in between these two lines. And so this bigger field here, as opposed to the three dots you saw before, is the actual separation to size fractions. And so we have coarser grains in the nearby soil and bulk material going towards here to till now I'll say an unknown source, and finer materials towards here. And the mixing is happening between the fine particles from the nearby soil and the volcanic rims in the lake sediments. And so let's first try to see, well, what is the source for this these granitic soils in a volcanic field? For that, we need to go back to the lithology. So I'll remind you again of this geological map that I showed before. And here is the lake, and here are alluvial, fluvial, quaternary sediments, and here are these granitoids, hint, hint. And so Chen and Yan compiled the isotopic composition of the granitoids from the Cathasia granitoids. And what we can see is that the isotopic composition of these granitoids fall very nicely as an extension of our nearby soils, or I should say that the nearby soils seem to be an extension of those granitoids. The field overlaps this way and also continues this way, but for the sake of making this easy to see, I didn't make this very big. And so I think we have the source for the soils, and what is really like the main thing that tells us that this is the source is that the coarse grains are the ones that are more similar to the granites as opposed to the fine particles. That means that the source has to be close. And the nearest outcrop of the granitoids to the volcanic field is about 50 kilometers. So we're really talking about fairly short distances. To be fair, the less deposits overlap the granitic compositions. And so if one were to just look at the isotopic composition and not look at the general area, you could say, or you could argue, that the less is contributing here. But this is about 2,500 kilometers away, and this is about 50 kilometers away. Putting all of that together, I would say this is a less likely source for this material. So I had first two questions to answer. Can I identify any dust in the lake? And I think I can actually identify some foreign or material that doesn't come from the lake rim into the lake sediments. And the source of the dust, I think, is the fine particles from those nearby soil that are derived from this granitoid, that accumulate from these granitoid fields. But can we say something about climate? And so, oops, that was a spoiler. Sorry. And so can we say something about climate? And now I want to just concentrate on this area here. And if you see that most of the change actually is happening in the strontium end of things and not on the neodymium. So let's see how strontium changes in time. So now we have strontium here on the y-axis and age of the samples in the core sediments on the x-axis. And remember that the radiogenic isotopes come from the granitic source, and the less radiogenic or the lower values come from a volcanic source. And I think that by looking at this, and when I first looked at this, I said, well, I have a general change, and I also have peaks in my samples. So what are these peaks? And very nicely, these peaks correlate with global climate events. And we can see here in the orange bars are Heinrich events, and we see the Younger Dryas. And so we already have a relationship to climate. Strontium doesn't directly represent climate, but we are seeing that all of these peaks do relate to climate. But why is that? And why is it that when we have Heinrich events, we have more input of granitic source versus a volcanic source? Well, Heinrich events are known in this area, or in other areas too, to create dry climate. And so we have, and that is seen in other records in the area. And so now not only that we can relate our peaks to climate, and that is the Heinrich events, instead of volcanic and granitic, we can also say dry or wet. So here's the other step towards interpreting this in a climate setting. So now when we have low isotopic composition, we're talking about wetter conditions, and when we're talking about radiogenic isotopes or radiogenic isotope input into the lake, we're talking about drier climate conditions. And I promise that I'll go back to the Yancheva study. So I think that, I don't know if just to use the word of fluke or whatever it is, the titanium interpretation that they had, I think there's a flaw in that system. But they actually are seeing a real signal because they see this dip in titanium, which they interpreted as high dust input from the less deposits. But we're also seeing this dry episode here. So they are seeing a climate signal. I just don't think that their mechanism that they're proposing is the correct one. And so that was in our lake. Let's see how we relate to the other regional records. We'll compare our findings now to the isotope record from Hulu and Donner. And so up here is the plot that you saw before of the strontium isotopes in the lake. And down here is a compilation of Hulu cave speleothems and Donga cave speleothems in green and in purple. And as a reminder, they interpret their data as summer and winter monsoon. We're interpreting it as wet and dry. And the first thing I'd point out is that the Heinrich events are shown in their record as well. And so
you don't see Heinrich in 4 and 5.
I don't have a high enough resolution for that. That's a good point. That is a good point. We're waiting for more samples to increase the resolution here. But I think these are fairly good ones. And so we're seeing that dry episodes are recording in both archives, and dry episodes in Huguangyan Maar correlate with winter monsoon influence in the Speleothems. So we're starting to see not just the climate indication in the samples, but also we can relate it through the Speleothems perhaps to the monsoon systems. When we look at the general trend in the data, and I just drew this by hand, by ignoring the millennial scale peaks, we can see that there is a general agreement between the two records. And where we see a transition in our record towards what we interpret as dry conditions, in the Speleothem record, we're seeing a transition towards a stronger influence of the winter monsoon. So by looking at the strontium isotopes in the lake records, I think we can divide it into two climatic modes. we have one climatic mode that is happening during, one mode is during strong summer monsoons where the granitic divide sediments accumulate in the vicinity of the lake. And during these wet intervals, the dominant signal in the lake is volcanic. And then our second mode is the dry episodes, the dry periods, where we have either a weak summer monsoon or a strong winter monsoon, during which the fine particles from the nearby soils are wind-blown into the lake, and that is reflected in high strontium isotopic compositions, high radiogenic influx into the lake. And so I mentioned before that there was this question about monsoon drivers. So I'll kill the suspension now. I'm not going to resolve this right here and now, but we do actually have some information that we think is going to, we're working on now. I'm actually working with Dolly on this these days, is to try to see where does our data fall in this bigger question. And so plotted here is the strontium data in the black plots. This is the plot that you saw before, age here on the x-axis, strontium here on the y-axis, and we have summer insolation 65 north plotted here in purple. And I'm marking here in general, this is a short course, so we can't really look at very long term, but just by looking at this, I would say that over here one might see what is anti-correlated with the insolation. And over here, and pointed out nicely, is that we don't have a very high resolution, but hopefully with more samples we will see this better. These might be going better with not anti-correlated to this part of the core. But the insolation is made of different components, and two important ones are obliquity and precession. And so when we plot our data and compare it to obliquity cycle and the precession cycle, we can actually see, and this is just by pure observation, is that the record follows or has a better match with obliquity rather than precession. And that is somewhat surprising considering the low latitude that we're in, because obliquity, you would expect to see a stronger obliquity signal in higher latitudes and a stronger precession cycle in low latitudes. And so this is something that we're still working on and we're trying to resolve, and to see which component of the different forcing can account for the signals. So stay tuned. So to summarize everything here, I know it was a full talk. I just want to point out that we had the provenance part of this study. So by using neodymium and strontium isotopes, we could identify the source of the sediments into Huguangyan Maar, and that is the bulk of the material comes from here, but we could also see the influx from these granitic soils, something that we couldn't see just by looking at the lithology, the mineralogy, or the general chemistry. And the increase in 87, 86 strontium ratios in the sediment indicates the aeolian input. So this has to be wind blown in to the lake. In terms of climate, we suggest that the low isotope ratios reflect periods of strong summer monsoons. And so we have a very strong signal just from the lake from itself, from the volcanic materials. And the high values reflect drier conditions or a weaker summer monsoon or stronger winter monsoon. We can't decipher between these two options by just looking at our data. And in terms of the climate forcings, it is possible that we're actually seeing a stronger contribution of obliquity at low latitudes than is observed in other records, and we're trying to figure more about that now. And so I'm not going to show any data from this, but just sort of as a teaser for the future. We have another lake, a Maar Lake, that we're looking at up here in northeast China. It's just above North Korea. And there we're also looking at the different sources, and I'm going to point out that this lake is the direct root of all these deserts, and we actually do see inputs from the different deserts at different times. And so by looking at both these records, we eventually want to look at a more complete picture of this area and where the monsoons are affecting or what systems are affecting what. And I would like to thank you for your time and for listening. Obrigado for a lot of patience and talking to me about this data, and everyone in the lab, Ophir, Daniel, didn't forget you, everyone in the lab for their help. And I'll be happy to take questions. Yeah.
Okay, so when you talk about the time series that you have, I know that you have worked with the language of construction, but then I'm just curious how the chronology has been reconstructed.
So I didn't do any of the dating for our core. This was all done by Minger et al. They used carbon dating for as far as they could, and then magnetic susceptibility to match the different cores. And so that's how it was matched. Yes.
So when you look at the provenance, right, you look at changes in strontium over time. Do you see the same things when you look at epsilon and neodymium?
Epsilon and neodymium showed a much weaker signal, and so we ended up not looking at that. And strontium showed a very strong signal, and so we went with that.
And if it's granitic versus basaltic, wouldn't you expect the neodymium to show?
That's a fair point, but we just didn't see it, and so we went with what was the strong signal. And I did look at the neodymium together with the strontium. I plotted them. We started with just a few set of samples before we do all of them, and we saw that they co-vary, but the change in variation is smaller, and so it was better to just look at the strontium.
Shikma, what will happen if you saw strontium concentration instead of strontium of strontium? If that's
I did that, and I can't remember what the plot looks like. But yeah. Right. No, we did that, and I can't remember, but I'll double check that again after we talk.
Maybe I missed it, but your alternate explanation for the increased input of less is drying changes between dry and wet periods. Does it explain the titanium signal?
So what I think is happening with the titanium is that it's a local weathering issue. So the basalt actually has titanium in it. And in their paper, Yancheva actually described that the basalt and all the volcanic material around is rich in titanium. But then they go to say that titanium comes from dust. And I think that the titanium is enriched because everything else is being washed out because these samples are so weathered. And that is what is causing the strong titanium signal in the lake. I did look at titanium variations over time, sort of as a time series like they did. We don't have the resolutions that they have because we actually dissolved samples. We didn't just do counts. And so our sample resolution is much smaller. What they did, I assume, is they took the core and then just measured every millimeter of the core. We didn't have that option. And I do see similar trends with them, but whatever the titanium is showing, it cannot show an input of less deposits. And if we look at this plot here, if we didn't have this potential source, one could argue that the values that we're seeing here come from input from less. But since we have these granitic soils here, and the core sediments are actually what is drawing the values towards granitic source, I just think it's very unlikely that the less is the answer. And I think by looking at other parameters in the chemistry, like organic content in the sediment, it seems like there's more complexity in the titanium than just looking at the values and saying, this means that. It means weathering, it means complexation with other things, it means mineralogy. There's just too much in there to look at it like that and say, this is what it is.
If there is titanium in the local basalt, how could they attribute it to the influx of the...
I didn't review the paper. I don't know. I think one of the problems maybe, or how it sort of, the system missed it, is that they're looking at counts and not at concentrations. And when you're looking at counts, it's hard to say, well, is this 1%? Is this 3%? It's just changing in concentrations. And so I think they're actually seeing a real signal. Like it happened, but the story behind it, I think, is not the correct one. Yes.
I'm not familiar with the geography of this region, but
yes.
Can it be that just by lowering sea level and exposing all the vast areas of the shelves in a specific area, that's what suddenly gives you the weathering material from the granite going inland?
So I think that would enhance what I'm saying, definitely.
But that means that there is a major thing on the big cycle.
Oh, so you're saying that in terms of
sediment.
Yes, and that actually is one of the comments one of the reviewers made. So it is something that we're looking at now is the sea level because yes, as sea level drops during glacial peaks, like you'll have more continental shelf exposed with more sediments, more weathering that can go into the lake. Dania?
If you would look at the strontium and neodymium signals, you will see that the neodymium does not show large variations, as you said. So maybe you have rather one source that is not changing through time that much. And what you do see in strontium isotope is the different weathering processes. As you said, wet and dry, but on a different scale, not because of the sources, but because of the weathering occurring on the reef.
So that could account for some of the change. And I don't have the values here to show, but variations that would come from the weathering processes that you mentioned wouldn't be this large. When we look here, and I compare it to other samples in other places in the literature, these are really large variations. You can't explain that by just different weathering processes. So it could be that together with something else.
The strontium concentration is very about different sources.
Right. Yeah, I did it, and I just can't remember what the plot looks like right now.
The same on the other axis, you have to show it together.
Yep, that's a good point. Thank you.
Thank you very much.
Thank you.